And we are back. Happy Thursday. And today we'll continue with a conversation pertaining and focusing primarily today on events and what is a probability. But before we begin, let's go over a few administrative bits. Now, certainly the reading, you're all well aware, by the 3rd of September are the first 4 pages in the Barron text and pages 9 through 14 in the Barron text from Chapter 2. Homework 1 has been out since the day before classes began. It will be due at the usual 11:59 and 59 seconds p.m. That's 1 second before midnight on the 1st of September, which is a week from Tuesday, the 25th. And so certainly it really depends on you. If you're doing a little bit of work every day, you're being well prepared, that means you'll be ready and carefree when it comes time for this homework, when it comes due. Or if you wait till the last minute, you will be anticipating impending doom. So the choice is really up to you. Please make sure you're doing work every single day. This is a marathon and not a sprint. Okay, so when we last met, we talked about what is uncertainty, and we motivated the point that uncertainty exists in everyday life. And there are certain types of questions or decisions you'd like to make, questions you'd like to answer. And we gave an example of a coffee shop when we showed an instrumentation system with an overhead camera that counted all of the customers that come into the store at every moment in time. And so certain types of questions we said that one might want to answer: how many customers visit the shop and when? How much coffee beans should I buy next week? How many employees should work each shift? How long will the drive-through line get? Or things like, how many food items will I sell next week? Now, all of these questions, the outcome is uncertain, but by gathering enough data, you can actually make informed and sound and optimal decisions from the information that you acquire from the overhead instrumentation that we showed last time we met. So let's talk a little bit more of the tools about how you describe uncertainty, and that's the focus primarily of today's sitting. So let's take a look at events and probabilities. Let's begin with some casual parlance. What is an event? Think about that. What is an event? Well, maybe it's something that happens. Is it something you see? Well, it's a little bit of both. Suppose I flip the coin, and when I do that coin flip, you can certainly say something happened, right? The outcome of that coin might be a heads, it might be a tails. But there's a little bit of a challenge here. Well, certainly, in order to have something occur, you have to see it. You know that famous saying, if a tree falls in the woods and nobody hears it, did it really fall? Well, observation is necessary in the measurement of an event. You have to see something. So if I flip a coin, you have to see that coin flip and therefore see the outcome of that coin flip. So that's one key part of an event. And an event is what we'll talk about when it comes to describing uncertainty, because the event is the thing that you see that is uncertain. So you flip a coin, and let's say it comes out heads. It resulted in something, and you saw that something. Well, is it always the case that you see a heads? Absolutely not. Sometimes it comes up tails. What if I had a coin, I flipped that coin 2 times, and both times it came up tails? Is it always the case that it will result in a tails? Absolutely not. So it can be heads or tails. That's what the non-determinism is that I talked about last time when we met. Is it the same each time? Yes? No? Well, maybe a little bit of both. The coin, same coin flip, the same coin, you flip it one more time, it's not always heads, it's not always tails. So we have a little bit of a problem here. If it's not always the same each time, how in the world do you describe this coin flip that you can observe, the outcome of that coin flip? Well, let's consider a different event. Let's consider rolling a die. A die has 6 sides. And let me ask you to think about this. Is it different from tossing a coin, that event? Yes, it is different. It's different because you have 6 different possible events that can occur, you can observe from the result of rolling a die, whereas with the coin flip, you only have 2 different possible events. So while they're both uncertain, they're uncertain in different ways. So we need a good way to describe all these different ways that these 2 particular types of systems, the coin flip and the die roll, that all the different types of observations you can make. Okay, how do we do this? Well, let me tell you. So an event needs a bunch of things, and this is a recipe for our class. Something that happens. You need an experiment or a trial. You need to do something. You walk across the street. You flip a coin. You roll a die. So you need some experiment, or as it's called, a trial, is that thing that gives rise to that observable. You need an observation. You have to be able to measure or examine the outcome of that experiment or trial. And then this last part is particularly important. You need to be able to describe how often you see these outcomes occur. Now, certainly, music has a lot of answers to many of life's questions. And I like to call it this: how often, when can I see you again? You're yearning, pining away to see this event again. When can I see this heads or tails? When can I see this 1 or 2, 3, 4, 5, or 6 too? So like many love songs from the 80s, you're pining away, yearning. When can I see you again? So you do something. You flip a coin, you roll a die, or maybe you take a picture, right? You have a 2-dimensional pixel array returned from your imaging element on your digital camera, for example. So you do something, you run some experiment, and you observe an outcome. Now, that outcome might be the side of a coin, the side of a die, or a 2-dimensional array of pixels from the digital camera. Given that, we already established that we don't know which of these outcomes will define the experiment or the system. For the coin, at one moment it could be heads, the other moment it could be tails. For the side of the die, 1 through 6, and for the 2D matrix of pixels, it could be all of the possible pixel colors in every position of the image that are available. That's quite a few large number of choices. So you don't know which outcome defines your experiment or system. And when that occurs, the best thing you can do is write out a description of the collection of all the outcomes that are possible. So, for example, we're going to do this for the coin flip experiment and for the die roll experiment. For the coin flip, we have the coin events. We can observe a heads, which we'll connote with an H. We can observe a tails, which we connote with a T. We also have die events, which we'll write out the numerals 1 through 6 to represent each of the different faces of the die that we can measure as the outcome, the faces that are pointing up as when the die comes to rest on some surface. So we have each of these events for the respective outcomes that are possible for these 2 experiments, the coin flip and the die roll. So mathematically, we have a framework for being able to write out collections of things, and these are sets. We're going to use set notation to write out those collections of events that are possible, all the possible observable events for each one of these 2 different types of trials or experiments. So we do this for the coin flip, and we'll write out the coin events. We have heads and tails. So in set notation, we have our curly braces, open, close, and a comma-separated list with the heads and the tails. Likewise, for the die roll events, those outcomes, we have set notation, open, close, curly brace, and comma-separated list, 1, 2, 3, 4, 5, and 6. So now that we have these sets, we can start to describe, at least at this juncture, all of the possible outcomes from these events of these experiments that is possible to observe. Now, the important thing is that you have to enumerate all possible observable outcomes. Okay, so these have a name, these sets. We're going to call them the sample space. And we're going to denote the sample space with capital omega, right? There's omega. And we're going to use a subscript in the notation here on the screen where, let me choose my pen, where the subscript represents the particular experiment for which the sample space enumerates or lists out all the possible observable events. So here, omega sub coin are going to be all the possible observable events for the coin flip experiment. That's heads and tails. And omega sub die, are going to be all the possible observable events for the die roll experiment. So that's the set 1, 2, 3, 4, 5, and 6. So now we talk about the sample space as being the set of all the observable events that are possible for a particular experiment. All right, so we have this omega, our sample space, and it has some number of events. Now, I listed out the events specifically for the coin flip and the die roll on the previous page, but if we wanted to abstract this more generally, regardless of what type of experiment we're running, let's call these events little e. So we have little e1 with a 1 subscript, e1 represents the first event, e2 would represent the second event, e3 would represent the third event, and so forth. So our sample space, more generally, omega, has some number of events, e1, 2, 3, 4, etc. Now, if we number these events, and you pay attention to the subscript, we can actually count them. We can enumerate them. We can figure out how many there are. Now, you'll notice here, when we write this subscript, the subscript means that you're associating each member of our sample space omega, our set of possible observable events. We're associating each one with elements from the set of the natural numbers. So there's a set of natural numbers there, 1, 2, 3, 4, and so forth, up to some number n. Now, of course, we actually write out this association. So the first event, e sub 1, we're going to associate with natural number 1. E2, we're going to associate with natural number 2, and so forth, up to and including some event number n, little n. And it doesn't matter what little n is. Little n could be anything. So we have this association, and when we pair the members of the sample space, omega, with members of the set of natural numbers in some natural ordering, we might have some maximum. In this particular case, the nth event, e sub n, is paired with the nth natural number, number n, and we see that the sample space omega, it stops, it ends. There's a maximum natural number paired with its elements in some ordering. So this number is called the cardinality, or the count, the number of elements in the set. So in this particular case, because we can draw a one-to-one correspondence between the set of naturals up to and including the nth natural number with each of the ordered events in sample space omega, and it ends at n, we say that the cardinality or count of the events in omega, i.e. the size of sample space omega, is equal to n. So this is the cardinality, or the number of elements in the set. In our case, in this example, our sample space omega, which is the set of possible observable events. So the cardinality of omega is n. Notationally, we'd write the following. We'd say n is equal to magnitude of omega, where we have these vertical bars enveloping our omega to represent the cardinality or the count. More formally, cardinality is the number of basic or cardinal members of a group. We're enumerating or counting them by drawing them to one-to-one correspondence with the set of natural numbers. Okay, so we're going to need this machinery, the cardinality, in order to describe more complex events. Now, certainly, it's very easy to talk about things like a die roll, and there's a plane passing overhead. It's certainly easy to talk about something like a die roll or a coin flip, but we need a way, more generally, and we'll talk about this a little bit later, how to enumerate or count the number of events in a more complex event versus the singletons like a coin flip or die roll. So let's try an example of this. How many events are in the set of n rolls of a die? We know that sample space omega for a die roll has 6 elements, 1 through 6. But how many if the event is n rolls of a die? So let's think about this. And again, we're going to follow this prescription. Something happens, we make observations, we're going to enumerate them, and then we're going to talk about this when can I see you again. That when can I see you again is our probability. Okay, when is the next time I'm going to see a particular outcome or set of outcomes within the sample space? So here's something that happens. This is our experiment. So we have here on the screen, we have n many slots, and it doesn't matter how many die rolls n represents, big N. Let me choose my pen color. We have our first roll of the die, our second roll of the die, our third roll of the die, up to and including our nth roll of the die. Now n, big N, the number of rolls, could be 10, representing 10 rolls, could be 3, representing 3 rolls, and could be 100 rolls, representing 100 rolls of the die. It could be 100. So in this first position, that's going to be the outcome of the first die roll. The next position is the outcome of the second die roll. The third position is the outcome of the third die roll, up to and including the nth position here is going to represent or store the outcome of the nth die roll. So now we have something happens. This is our experiment. You sit there, you grab a die, and you roll it n times. Each of those times you roll it, you record what the outcome was for each of those n many rolls, big N many rolls, and that's going to be your experiment. Okay, so what are your observations? Well, we know for a single die roll, we know that the cardinality of that sample space omega is equal to 6. We know that, but that's for a single die roll. Here we have n of them. So we can use that fact for each of our n many die rolls. And we know that the first roll is going to have an outcome of 1 or 2 or 3 or 4 or 5 or 6. And then for each of those possible outcomes, we're going to have an outcome in the second roll of 1 or 2 or 3 or 4 or 5 or 6, and so forth for the third die roll up to and including the big nth die roll. So these are all of our observations. Okay, well, let's write out the number of choices that we have, i.e. the number of possible observations for each one of those rolls. So we have 6 choices that we can have for the first die roll. We have 6 choices that we can have for the second die roll, 6 choices for the third die roll, up to and including 6 choices for the big nth die roll. So we have big N many die rolls, and for each one, there can be 6 possible outcomes that we can observe. So what do? Well, we multiply, because for each one of those choices, let's say you have a 1 for the first roll, right? So let me just circle that, a 1 for the first roll. For that choice of 1 here, you can have 1, 1 for the second roll, 1, and then 2 for the second roll, 1, 3, 1, 4, 1, 5, 1, 6. So because of that, we multiply the number of choices together for each one of these options, right? So we have 6 choices for the first roll. We multiply by 6 for the 6 choices of the second roll, times 6 times 6 choices for the third roll, and so forth. So we're going to multiply 6 by itself, big N, many times. And so when you multiply a number by itself n many times, that's the same as exponentiating it to the nth power. So that means for n many die rolls, we have a total of 6 to the n, the big N, many patterns of 1 or 2 or 3 or 4 or 5, 6 of those 6 choices here, 6 choices here, 6 choices here. So we have a total of 6 to the big N power many choices here. So let's take another view of this, and I'm going to draw out an expansion of the die roll. Suppose you have your first roll, roll 1. Now, your first roll, the outcome could be 1, 2, 3, 4, 5, or 6. Okay, so here's a 1, here's a 2, here's our 3, here's our 4 event, here's our 5 event, and here is our 6th event. Now, of course, after this first roll, you're going to take roll number 2. And if your outcome of roll number 1 is 1, for roll number 2, so there's our roll number 2, I could have a 1, 2, 3, 4, 5, or 6. Likewise, for each of these rolls, I can have 6 outcomes. So I'm only going to draw that last one for an outcome of roll 1 of 6. I could have for my second roll an outcome of 1, 2, 3, 4, 5, or 6. So that would be a 1 is my 2 outcome for the second roll, 3 outcome for the second roll, 4, 5, 6. For that first roll, if my outcome were 6, I could have a second roll outcome of 1, 2, 3, 4, 5, 6. So now if we take a look at this, for the second roll, well, for the first outcome we have 6, for the second outcome we have 6, for the third outcome, 3, the second roll we can have another 6, we could have another 6, we could have another 6, we could have another 6. So we're going to have 6 plus 6 plus 6 plus 6 plus 6 plus 6 possible outcomes after 2 rolls, right? That's 6 times 6, which is 36, or 6 squared. And then each time here, for this 6 squared, these 36 many outcomes, for each of these, if we take a third roll, roll 3, we're going to have 6 for each of these. So 6 here, 6 here, 6 here, and so forth. And so we multiply because of this combinatorial expansion. For each of the rolls, on the next roll, we have 6 more, so we multiply by 6 each time the number of outcomes from the previous round to get the number of outcomes possible for the next round. And so if we were to count these, right, that would be a roll outcome of 1 for roll 1, 1. That would be a 2, a 1 followed by a 2, a 1 followed by a 3, a 1 followed by a 4, 1 followed by 5, 1 followed by 6. If we pursue this bottom edge, roll 1, that would be a 6 for roll 1, followed by a 1 for roll 2, a 6 followed by a 2, 6 followed by 3, 6 followed by 4, 6 followed by 5, 6 followed by 6. And so we multiply because every time we take another roll, for each of those previous possible outcomes, we're including another 6 outcomes. So it increases so-called multiplicatively. Okay, so we know that the cardinality of a single die roll is 6, and any outcome can appear. We further describe how often we're going to see a particular outcome, right? You do something, that's our step 1 in our prescription. You observe something, that's our step 2 for a particular outcome. Now, this when can I see you again talks about the degree to which an event is probable. When can I see it again in the future? What is the proportion of the number of times, if I keep doing this experiment, for which I will see this event outcome again? So this is what is probable. And when we talk about what is probable, this is the degree to which something is probable. We describe it by, guess what? The probability. Okay, so that means if something has a higher degree of what we'll call when can I see you again, we're going to see it more often. So that means the proportion for that event is going to be larger. Now, of course, when you express proportions, you want to normalize it, express it on the same standardized unit. Now, we do this with a percent. Percent comes from the Latin per centum, where centum is the Latin word for hundred. So when you talk about percent, you're really saying per hundred. And so the reason why that's done is so you can make a like-kind comparison. Suppose if I said to you 50 out of 100 times I saw something happen. Well, you would say 50%, right? Or 50 out of 100. If I said 250 out of 500 times I saw something, well, how do you make this comparison? 250 is not equal to 50. Well, you do it in this per centum, and you shrink this down to a per 100 scale, that means 250 per 500 is the same as saying 25 per 50, which is the same as 50%. So by shrinking it up or shrinking it down and making it per 100, well, really would say 25 per 50, you divide by 10 and you multiply by 2, and you get 50 per 100, and that's 50%. So this percentum or percent allows you to take arbitrary proportions to 50 out of 500, 50 out of 100, and express them in the same scale or the same units so that you can make a fair comparison. Okay, so let's introduce a little bit more machinery. One where each outcome or each possible outcome is equally likely. That means if you do something a large number of times, run that experiment, make an observation, that each of the possible observations will have equal proportion, right? When this happens, that's called random. Random, the definition is that no one outcome is preferred over another. They all have equal representation proportionately as you run experiments and make observations. The opposite of random is something called biased. Biased means that some outcomes are preferred over other outcomes. So henceforth in your conversation, when you say, oh, I just had this random thought, it's not a random thought, it's a biased thought. So nonetheless, we have our sample space omega sub die, 1, 2, 3, 4, 5, 6. Its cardinality is 6. And so if we have equal preference for the outcomes of the die, it's a so-called fair die. That means that each of the sides of the die are equally preferred to one another, equally likely. The when can I see you again is the same proportion per centum. And so equal preference means equal percentage. And we write the probability of that event, the outcome of a die roll, is 1 over the cardinality of that sample space omega die. So we know the cardinality of sample space omega die is 6. So 1 over magnitude omega die is 1 over 6, or 1/6. Okay? All right. And so this is what a probability is. And for a random or fair die, we get per centum 1/6 as the probability, defining the when can I see you again for each one of these outcomes, the first outcome, second outcome, third, fourth, fifth, or sixth. Okay. So let me go back to that complex event involving Bn many rolls of the die. We asked, what is the probability of a given outcome, event E, from n rolls of a random die? So now we're bringing in some more notation. Random means that it's a fair die. All of the outcomes are equally likely. So what is this probability? Well, that would be 1 over the cardinality of omega n rolls of a die. Now, I'm not listing out omega n rolls of a die. I'm just noting it, but we can certainly calculate, which we did before, the number of outcomes. That was 6 to the big N power. So that's 1 over cardinality of omega n rolls of the die, which is 1 over 6 to the n power. So that means for n rolls of a random die, it's a pretty small chance to be able to guess a particular outcome of n rolls of a die. So if we had 10 rolls of a die, it's like asking what's the probability if you roll the die 10 times that you're going to get 1 10 times, or you're going to get 1, 2, 3, 4, 5, 6, 1, 2, 3, 4 as the outcome of your n rolls of a die. So if you think about it, it's a very, very small event. The when can I see you again is going to be very, very tiny because you're not going to see this thing again very often. Okay. So let's take a look at outcomes and sample space, and we need a little bit more machinery to complete the conversation for today's meeting. And so we have our sample space omega, and then we also need the empty set. Empty set is this notation, and it talks about the event where nothing happens, the nothing event. We need that to complete our machinery. And then we have the probability of an event, P of E, and we're going to use curly braces to match what's in the book. It's the probability of some event that describes this when can I see you again. The proportion of times when you perform an experiment where the outcome you observe is a particular outcome described by your event E. And the sample space omega is a collection of all possible observations or events that you can have for a particular system. So this probability is the when can I see you again expressed per centum or percent. Okay. So let's segue to a little bit more MATLAB instruction. And in this particular technique I'll be showing you is a method for simulating simple events. Okay, and this technique is something called stick breaking. And we'll first motivate what stick breaking is on the drawing pad, and then we will code it up in MATLAB. So it's called stick breaking. And it's used for simulating a random or biased experiment. So here's the backstory. So you have a person, and this is you. Certainly my artwork is not going to set the world on fire. And you have a stick that's on the ground here. And maybe this one has a leaf attached to it. Okay. And the stick has some length to it. It doesn't matter what that length is. Now, you have what I'm going to call breaks. And these breaks are going to be partitions that literally break apart the stick. Okay. Some breaks are smaller. Some breaks are larger. Maybe some breaks are really, really small. And some breaks are the same length. So we have a break here, 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 and here. Okay. So now each length of this broken stick is going to have some length, and that's going to be a weight. Let's call this weight 1. Call that weight 2, weight 3, weight 4, and weight 5. And let's assume that this person is going to throw a ball. Going to throw the ball up, and it's going to land somewhere, this ball, on the stick. And the probability or proportion for which the stick is going to land on a particular break or region of the broken stick is going to be the probability associated with that particular break. So the proportion here will be W1. The proportion for this one will be W2, and so forth, W3, 4, and 5. So we're going to use this construct to simulate a biased experiment, and we're going to start out with each segment of the stick corresponding to one outcome of a die roll. So in our experiment, we're going to have a W6, and the first region of the stick is going to correspond to a die roll of 1. The second region of the stick is going to correspond to a die roll of 2. The third region of the stick, die roll of 3. Fourth region, die roll of 4. Fifth region, die roll of 5. And sixth region, die roll of 6. Okay, so that's going to be our simulation. Okay, so let's exit the PowerPoint and keep the annotation, and let's bring up MATLAB, and let's implement our stick breaking. So let's start a new script, and this new script is going to be called, let's just save it first. Let's call it die roll stick. breaking. Okay, so we're going to start out. Let's, for good measure, put a few comments in there. And let's say stick breaking construction for single die roll. Okay, so the first thing we want to define is the stick weights. And the stick weights, we're going to make this an array of numbers. And these numbers, it can be anything, but they're all going to be equal, right? So let's just say 10, 10, 10, 10, 10, 10. And these weights are going to represent those weights for the segment of the stick that I alluded to before. So now we're going to take these stick weights and we're going to do something called normalizing them. You don't have to normalize them, but I choose to normalize them. So we're going to create a normalized version, norm stick weights. And let's first save total weight. Total weight is the sum of all the stick weights. Okay, so now our normalized stick weights, we're just going to rescale it to a scale of 1. It's just going to be stick weights divided by total weight. Okay, so I like to, as a matter of practice, have a display done at the end because it gives me an executable statement in which to set a breakpoint. So let me go ahead, save this, and let's test this out. So if I run this, I misspelled W-E-I-E-I-G-H-T. There we go. I have a little bit of a typo. So let's save that again. Let's run it. And if we look at stick weights, it's an array of 6 elements or vector. Each element has 10, and it's the weight associated with each of the 6 lengths of the broken stick. And we have the total weight is the sum of all of that. That's 60. And then when we take the norm stick weight, it's 0.1667, which is 1/6 expressed as a percentage. Okay, so that works as you'd expect it to. So now let's set something called a cursor. We're going to have one called the high end, and we'll set that to -1, and another cursor called the low end. We're going to set that to whatever high end is. And what these cursors are going to do, they're going to allow us to check the bounds of the stick for which region that we've encountered based on a random selection. So let's go back to the PowerPoint and let me illustrate what I mean by that. So we'll bring back up the PowerPoint and come back to our stick breaking construction. Let me set the pen, and I'll set the pen color here to black. So we're going to start out with a cursor. One is called high, and another one is called low. Now, high is going to represent the high end of a stick region. Low is going to represent the low end. We have a weight, and we start out high is equal to low. And on the first round, we're going to add to high whatever the value is associated with that region of the stick or weight. So we're going to take high, and we're going to move it in the next round. So that's time 0. At time t1, we're going to say high is equal to high plus whatever the value is of that first region, which is weight 1. So once we do that, low is going to be at the beginning of that stick, and high is going to be here. So then we randomly select a value that's going to be our toss of the ball, and we're going to check to see if that ball is in the region between high and low. If it's not in the first region between high and low, what do? We set low equal to high, so low is here, and then we add to high the value of the second region. So that puts high over here. So we keep doing this and then checking again if the ball had a value that landed between the current value of high and low. So if it's between the first value of high and low, we select this first outcome. If it's in the second region marked by high and low, we select that second value. So that's what we're going to do next. We're going to set this up with our stick breaking. All right, so let's keep those illustrations. Let's go back to MATLAB, and let's continue on. So high is equal to -1, low is equal to high end, or actually, I should set the low first, just to be correct. Low end is equal to -1. Nope, that's correct. All right, so now the next thing we're going to do, let's have a loop, and let's look at the number of elements or positions we have in the array. Num breaks, num regions is equal to length of stick weights. Okay, so let's save that and test it out and look at what we have so far. Oops, let's see. Num regions. TH, typo. All right. So let's look at num regions. There are 6 of them. Okay. So now we're going to loop. For I goes from 1, increment by 1, to num regions. And in MATLAB, arrays are 1 space, not 0 space. So we're going to iterate through each of these regions. And the first thing we're going to do is randomly select a value between 0 and 1. Because we've normalized it, the value goes between 0 and 1. Okay, so we're going to select a random number between 0 and 1. So let me try the help random. And random gives you an array of numbers chosen from one parameter probability distribution. And random, let's see, I don't want to talk about distributions just yet. Help rand. Let's look at rand instead. So it gives you a number between 0 and 1. Okay. So if we call random rand, it gives you a number between 0 and 1. Call it again, call it again, call it again. Okay. So we're going to call rand, and let's call that ball toss is equal to rand. Okay. And so now we set in the beginning low is equal to 0. Low end is equal to 0, not high end. We start at 0. High end is equal to low end plus norm stick weight, the ice position, right? So if we do that, well, what happens? And then let's see. Okay, so if we do that, we'll first start out low is 0, high is low, high is, okay, high, and yeah, that's right. High is low end plus the norm stick weights. So that's our first position. We're going to check now to make sure, to check if this ball toss is between high and low. If ball toss is greater than equal to low end, and at the same time, ball toss is greater than high end, then what? That means the ball is in that particular region, representing that break on the stick. So that means selection, let's just select, selection equals -1, and we say selection equals I, and then we stop, break. Otherwise, you're going to continue. Okay, so let's just say end. We're just going to keep continuing. Now, of course, we're going to do two different things if we reach the end, because you don't want to say, oops, this is incorrect, greater than equals less than high end. It's a typo, the bug. If you're at the last region, if I not equal to num regions, if you're not at the last region, do that. Else, you don't want to use less than high end. You want to use less than equal to high end. So if ball toss is greater than equal to low end, and at the same time, ball toss is less than equal to high end. And the reason for that is because we have half open intervals, but if you get to the last stick break, you want to include the end point. And so if that's the case, break, selection equals I, and then break. Okay. So now we have set up the selection of the regions of the stick. So we're going to put a little bit of comment in here. So we're going to say iterate through each piece of the stick and check if the ball landed on it. Okay. So this one says, if you are not on the last piece, check half open interval and else if you are on the last piece, check the closed interval. And this is half open on high end. Okay. Okay. So we have our checking of the regions of the stick. We stop if we get a selection, if it lands on a particular region as marked, whose endpoints are marked between high and low, and we iterate over each one of those regions. So now that we have a selection, let's look at our selection, and we're going to print out what each one of those values should be. So we're going to say stick, let's see, the events corresponding to the region of the stick. Let's say that's 1. If it's a die, 2, 3, 4, 5, 6. Okay, so we have some text here in what's called a cell array, and we're going to index that cell array in a print message. So message equals formatted print. Die role is %s for string, and we're going to say the events selection, that index that we had. All right, so now I'm going to display message. So let's try this out, run it, and see what happens. So let me show more of the screen here. We start out, we define our stick weights, we have our event names, num regions, the number of regions that we have, so the number of outcomes, each one of these weights. We have the total weight, we normalize to cast it from just all tens to a proportion between 0 and 1. We mark our cursor, high end and low end. We do our ball toss. We iterate through each region on the stick, do the bounds checking, and then print out the requisite message. Okay, so let's take a look first at what our ball toss is. So if we run that, well, our ball toss is 0.6324. So let's step through. High end is equal to low end plus num stick weights, plus norm stick weights. So the high end, low end starts out as 0, and high end should be 0.1667. So if we step here, low end is 0, high end is 0.1667. So we know that our ball toss is not between those bounds. Okay. Oops, we made a mistake here. We're forgetting one key step. At the end of the loop, we're going to set low end equal to high end, right, to move that cursor forward. All right, so let's save there, run. So let's come down here. Let's step. High end is 0.1667, low end is 0. So we're going to do our bounds checking. Our ball toss is 0.0975. So we step and we check to see if ball toss is between low end and high end. So ball toss is greater than equal to yes. Is it less than high end? Yes, it is. So if we step here, selection, and break. So if we do our print, let's see what happens. Step and step. The die roll is 1. Okay, so let's try this again, and let's see what we get if we have another roll of this die, virtual roll of the die. So let's step. Our ball toss was 0.27885. So that should be in the second or third region. So step, high end equals low end plus, okay, that's the first region. So it's not in the first region. Low end is high end. So in the next round, low end is 0.1667, high end is twice that, 3333. That should be where the region corresponding to our flip. So let's check. So step, yep, it is. And if we do our display, die roll is 2. Okay, great. So now we have the routine. So we want to make sure high end is 1 and low end starts out as 0. Selection starts out as -1. Okay, so let's move low end equals 0 here. Let's move ball toss further up. Let's move this stuff further down. Okay, so now what I'm going to do is I'm going to, over some number of rounds, keep tossing the ball, right? I'm going to toss the ball several times, and I'm going to do this coin flip some number of times. So I need some way of iterating over some number of rounds. So I'm going to take all of this, including the display, and I'm going to indent this. Let's see. I'm going to indent that. Okay. So now I'm going to say num rounds equals, let's say 10 rounds. Okay. And so for R, the round number equals 1, 1, up to num rounds, what am I going to do? I'm going to do all that stuff, the print and the single roll of the die, and I'm going to say end. Okay, so basically what this implements for me is I'm going to do this stick breaking construction, num rounds many times. I'm going to randomly toss the ball. That's like our, and I'm going to then check the bounds of the breaks on the stick where this ball may have landed. Okay, so let's clear memory, clear the console, and let's see how we do. So die roll is 4, 6, 1, 6, 3, 5, 1, 3. Okay, so let's try that again. 10 times. Let's try that 10 times again. So 6, 5, 4, 1, 6, 5, 5. A lot of fives here. So let's try that again. Try that again. And try that again. Try that again. A couple ones. Try that again. And so this is a simulation for die rolls. Now, what happens then if we want to bias this die? Suppose I made the 1 outcome, let's say the 3 outcome. Instead of 10, I changed its weight to 1,000. Its weight is much, much, much higher. Watch what happens to the proportion of the number of 3s that occur in the die roll. Okay, I'm going to do this again, die roll 10 times, num rounds, right? We get 3s most of the time. Oh, we get a 2. We get sometimes not. Look what happens when I make this maybe 100. Okay, it's biased 10 times as much as all the other individual choices. You notice you get a lot more 3s. Okay, so this is the so-called stick breaking construction. And the nice part about this is you can implement a system, whether it's a coin flip, a die roll, or what have you, quite easily. And you can assign weights for each region on the stick arbitrarily, and in so doing, make it very easy to change the biases. It can be random, meaning all the weights for the regions on the stick are the same, or it can be biased, meaning that the weights for the corresponding regions on the stick are all not the same. So this is a so-called stick breaking construction, and what I've demonstrated to you is a simulation of the die roll for both the random and the biased experiment for the die roll. Okay, so with that, we will end there. I will see you all on Tuesday. Please make sure you're looking at the homework and working on that, and also make sure you're keeping up with the reading. As always, stay healthy and stay safe, and I will see you all on Tuesday.